All right, everyone. I hope you enjoyed the networking lunch. Let us go ahead and get started on our last session for the symposium and our session for the afternoon. So I'd like to bring up Jonas Hügel for this portion here. So please welcome Jonas. Take it away.
Thank you for the nice introduction and for the opportunity to present our approach to create precision post-COVID research cohorts based on I2B2 data. We are need to click in here. So now it's working. Okay. For the agenda, I will start with the presentation of the algorithm, and in the first 20 minutes around that, then we have a short time for question where you can ask question about the algorithm before we then go to the presentation of the synthetic data sets that we're using in the hands-on part. And then we are switching to the hands-on part where we apply the algorithm on the synthetic data. And afterwards, we will still have time for some Q&A. Okay, let's start with the algorithm. What was our motivation to develop an algorithm to identify patient-specific post-COVID symptoms? When you take a look, so this is an order graphic from around, I think 2003. We see that we have a lot of different COVID studies, and all of them use different definitions of what they are considering as post-COVID. That makes it really difficult to compare the results of these studies, but and also, not only making it difficult to compare the results, but also to find a common ground on the definition. What do we actually see as post-COVID? One reason for that broad range of different definitions is that a lot of different healthcare organizations have their own definitions, for example, the WHO, the NIH, and so on. All of them have slightly different definition of what is post-COVID. We decided to use, for the WHO definition, who defines post-COVID as a continuation or development of new symptoms, usually 3 months after the initial SARS-CoV-2 infection, where these symptoms are at least ongoing for 2 months. And now we come to the trickiest part of the definition with no other explanation. Implementing an algorithm who finds symptoms that occurring 3 months after, usually 3 months after the COVID infection and are ongoing for 2 months is quite easy. If you want to now implement no other explanation part, it gets challenging. To do that, we used data from the MGB I2B2 instance, where we extracted around 85K patients who had a COVID infections, which is our cases group, 170K post-pandemic control who had no COVID infection in the EHR record, and a 40K pre-pandemic control group which had a viral infection in 2018. And then for each of these groups, we used at least 1 year follow-up data. So for our pre-pandemic control, we made sure that this control group ended the data that were included before the 2020, and 3 years of historic data. Okay, so how does, for this data, we here see like one exemplary patient from these cohorts, in this case from the cases group, because this patient has a COVID infection, that we see in this with this turquoise C, and which the patient had an acute infection, and then he has a lot of other entries. At first, when we exported this data, these were ACT codes from the I2B2 instance, which we mapped to CCSR categories, which we used in the later on because it's reduced our feature input space from more than 10,000 features to around 500 categories. But we also did not use the raw CCSR codes then for the implementation of the definition. Instead, we first mined transitive sequential patterns using the TSPM algorithm that we developed in before to combine like entries of these CCSR codes to one pattern. So what the TSPM algorithm does, it takes one for each concept, it combines it with a later concept to a pattern of the length of 2. So if we take a look here at the first one at x1, that gets combined with x2 to a pattern with x3 and so on, and with the corona infection, with this concept which is called J, which is a possible post-COVID candidate, and so on. And that we did that for all these entries. We mined all these patterns. And that's what we used as ground truth or as input database to implement the WHO definition, because we then just translated the WHO definition into TSPM pattern. Okay, some nomenclature. So DCJ describes the distance between concept C and J in the pattern C to J. DJJ is analog the distance between J to J. ρxj describes the span and rank order correlation between the concepts X and J under consideration of the duration of this pattern. Using this nomenclature, we can now write the WHO definition. We can translate it like from plain English to TSPM patterns. So at first, so that we have a possible post-COVID symptoms, it must occurring after the acute phase, so it must exist in the patient record, which means we have a pattern that starts with COVID, ends with our candidate, where the duration is larger than 15 days. Then we say this possible post-COVID symptom is also associated with COVID-19, which means the correlation from the pattern that starts with COVID and ends with this candidate has a significant correlation when we consider the duration of this pattern. The next step is that this symptom should be persistent for 2 months or longer. This means we have a pattern that starts with COVID and ends with J, and another pattern that starts with J and ends with J, where the duration between J to J is larger than 2 months. And finally, we come to the exclusion criteria. That means for all other patterns that end with our possible candidate and starts with any other entry, the correlation is for this pattern under consideration of the duration is insignificant, which means J is not associated. J is not associated with X under this time distance, and therefore J can also not be explained with X. That's so. And so if you have like a significant correlation, that's not an explanation, but it's a good enough hint in the right direction that we say, if it's associated, it's near enough to we can explain it. It might be a reason for it. This X might be a reason for symptom J. But now I talked a lot about all these symptoms and these correlations between these patterns. How did we calculate all these correlations? Therefore, we at first identified all possible candidate post-COVID symptoms, so all J's, by just mining all patterns that started with a COVID infection and ended with something else. Then we extracted all patterns that ended with a possible post-COVID candidate, so from the cases and the control groups, so there we included the controls. Then we assigned a duration bucket based on the duration of this pattern based on the duration of this pattern. So we had like 4 different buckets, one for the duration between 0 and 14 days, so it's somewhat co-occurrent. Then we have between 14 days and 1 month, 1 month and 3 months, and a pattern duration from larger than 3 months. Then we merged all possible candidates with the corresponding duration bucket of this pattern, and then computed the Spearman correlations for all patterns that started, with something, with any event, and ended with a possible post-COVID candidate and the corresponding duration bucket. We applied a logistic regression to determine significant cutoff values and based on chart reviews to identify for each pair between, for each pattern and duration pair, individual cutoff values, so that we say, okay, for this, so that we can say, okay, that this is really really associated or correlating with each other, and therefore associated with each other. Okay, that's the foundation for the algorithm that we apply, and that we will apply later in the hands-on scenario, in the hands-on session. In the hands-on session, we will have a patient that where we extract, which is extracted, for example, from an I2B2 instance. This patient again has different entries in his record, which are mapped to CCSR categories. And in this example, this patient has like 3 different COVID infections. And we wonder now which of these infections, after which of these infections, post-COVID, the patient got post-COVID. Therefore, we had identified 3 different possible post-COVID candidates in this patient. And we then just apply our translation of the WHO definition onto these patterns to rule out every candidate that is associated with something else. So this is now the patient where we see all these calculated temporal associations. If a line is dotted, the association is insignificant. If it's a full line, it's significant. So for a better overview, only the relevant associations are included in this figure. Now we can easily say that J1, for example, is a post-COVID symptom, since J is associated with the COVID infection. It's persistent, so we have another J1 2 months later, and it's unexplained by other records. So for these J1s, there is no other earlier record with a significant temporal association. For J2, we can easily check and see that we can exclude it for the lack of persistence, because even if it is associated with the COVID infection, it's not ongoing, which is demanded by the WHO definition, and therefore it's not a post-COVID symptom for us. Then we also have J3. J3 is associated with the COVID infection and is also ongoing for 2 months. But we see that it is associated actually with the previously event. Therefore, it's probably explainable by this event, and therefore can be ruled out as a post-COVID symptomatic. If you are doing this for all the patients, what we're doing with our algorithms, we get a list of patient-specific post-COVID symptoms for each patient, including the duration of this pattern, which tells us how much after the infection this symptoms actually occurred. We evaluated this algorithm based on chart reviews and got a positive predictive value of 0.788%, and afterwards mapped and grouped the found symptoms by body symptoms. This is just an example for the endocrine system or for the respiratory system here, and we can also, due to that we have the duration of these patterns, we can easily see when these symptoms first occurred after the COVID-19 infection. So Yeah, this method is open source and quite easy to apply since we provide a hands-on guide. We have all the source code available on GitHub. There's also the manuscript if you want to take a look at it, but we also have a Docker container available where everything is pre-installed, including the enact to CCSR mapping table, and also the TSPM algorithm and everything. But we will not use like this Docker container now in this workshop, but instead we will use the POSIT cloud so that we can do it online and you don't have to download or install everything, so we can just do it in a web browser. But we will follow the extensive hands-on guide. Since we somehow need data for that, we created a synthetic data set, or better, I had a student who did that in a lab rotation, who created based on Synthea. Created a data set where we added additional, where we used the Synthea COVID-19 data set, added additional COVID-19 infection and post-COVID symptoms, converted it from SNOMED to ICD-10, so that we can just put it into our algorithm. If you want to know more about this algorithm, how we created the data, there's also the code for that is available on GitHub, GitLab. So yeah. Okay, but how does the input data look? Yeah, in general, it's quite easy. We have a table that consists of a patient name, start date, and PhenX. PhenX is possibly phenotype X, which is nomenclature from the Mello R package, which we also worked on. But if we translate PhenX or replace PhenX with concept CD, it looks like an extract from the observation fact table from the I2B2. And that's actually what we used mostly for as our input data types. Then we also have some demographics, which are patient name, age, sex, race, ethnicity, and the Charlson index, which are most also from the patient dimension table or can just be calculated in the I2B2. So that's our input data that we are using. Now, for the workshop, it might be, so you should create an account on the POSIT cloud, and just a free account, and then you can join with the second, with the long link if you want to type that, or use the shorter one below. You can join our workspace where we can then start applying this algorithm. But now also where you are joining, so if you now want to join the workspace, you can do that, and also there's time for questions regarding the algorithm before we go to the practical part.
Thank you very much, and wonderful work, very impressive. But one concern would be, when you look into the, chronic, COVID-19 long, there are at least 2 or 3 ongoing processes. For instance, have you also record, is that subject they already vaccinated or not vaccinated, and what kind of vaccination they have, and also I believe you already had some pre-existing units of the subject recorded, and then you try to exclude those confounding variable. For instance, if you look into the Pfizer or Moderna vaccinations, you probably recall they are just around 90% protective. So what happened to those, leak out like the 10% or so? They have 2 things ongoing on. One is the infection of the COVID-19. The second is that this is not protective. So I don't know whether the symptom coming from the underlying disease, the infection itself, the virus, or maybe coming from the vaccine, adverse event.
Yeah, okay. So if this adverse event is like occurring multiple patients and it's correlated to the vaccination, then it would be like a positive correlation. Then it would be a significant. If it's a significant correlation, then the vaccination would be an explanation for this possible post-COVID symptoms, and therefore it would be ruled out.
Yes.
So yeah, that's what the algorithm would do.
I understand your methodology because people always use the same thing. We look into the temporal relationship.
Yeah.
Before, after, or during, or what is the correlation there?
So
sometimes it's very difficult to tease out. For instance, maybe I already get a COVID-19 first, and then I go to CVS store and get to a jab and get the vaccination, and then suddenly there may be some symptom not appearing right after, except the pain of the.
yeah, okay. So it
you
really
know what I
depends.
think? Yeah.
It really depends where you're going and if
Right,
it's ending
too
up in
many
your
variables.
HR.
Right?
Yeah. So yeah, it's not perfect. So we cannot record everything. So we cannot catch everything, and also it's similar to pre-existing symptoms. We did not really. That's also a limitation. We get not if
Yes.
pre-existing symptoms are worsening. So that's also something the algorithm cannot record. And I think well, it's a scenario you described that you got the infection before you got your, and shortly afterwards you got your vaccination. That's a use case that's a case that's not really covered. So in this case, the symptoms will probably be assigned to the COVID infection and not to the vaccine. If you have your vaccination like in your record and it's occurring then later and this symptom is associated on the temporal distance with the record. So yeah, it's all about like also the date that is assigned to the record in the EHR or in the ITB2.
Right.
Because that's used to mine these patterns.
Yeah, I absolutely agree with you. I have no complaint, but just to think about, be careful when we interpret, the symptom, because you say, hey, you have the chronic, long COVID long symptom. I can equally say, well, we could also have the long post-vaccination symptom, which can, intermingle and mix together.
Might also be something, yeah,
very
that's
difficult to tease out.
yeah.
Thank you.
Thank you for the questions.
I do have a question from the chat asking, and what if there are multiple infections or non-cleared infection?
Yeah, actually, if the infections are more than, if the infections are not more than 90, if there's not more than 90 days between two infections, we consider those infections like as one infection with the earlier start date. So those, if you have multiple positive lab tests, they are aggregated into one with the earliest date. So that's considered. And the second one was part of the question was non-cleared infection. Yeah, if you have a non-cleared infection, so that's not the case for all of the patients, but that's why we demanded that the symptom occurred at least 14 days after the infection in the record, so that most of the patients have cleared their acute phase. And if we are seeing that a symptom is occurring quite shortly after the infection, so we get the duration. So if it's occurring in the temporal bucket like 15 days to 1 month, then it's probably also, you can think about if it's really a post-COVID symptom or is it still like a symptom of the acute ongoing infection. But that's something that you then need to rule out for each patient individually by just checking their patient record. So that's nothing the algorithm can do. But yeah, but good question. Thanks for that. Okay. So if now we had hopefully enough time that everyone could create an account, and we can go here. I can, perfect. Why is it not mirrored anymore? Just need to share it again.
And actually, while you get that set up, Jonas, I guess I'll make a plug for the symposium feedback survey. So there's a QR code on your table tent, and there'll be some information online as well about filling that out. And that helps us understand better what you're getting out of these symposium, what you'd like to see more of, all of those good things. So please do provide your feedback.
Perfect. After clicking on the second link, all of you should somehow end up on this web page where you see like the past workshop thing. This is in this R project, we copied, cloned the relevant parts from the GitHub repository of this long COVID AI scripts, which has some more scripts, but we only kept those that are now relevant for the workshop. So don't wonder if you take a look at the GitHub repository, there are more scripts in that repository, because if you take a look at our guide, which is also linked, you will see that we have like different guide for the case that you have enact codes or non-enact codes. We, in our case, follow the non-enact code guide here. So that's why we are using only a subset of the scripts. Okay, if you are in the POSIT cloud, you can click on the PASC workshop to open the project. And it's slowly loading. Okay. And then I can close these 3 files and open, and you will probably end on this level. You will find in the data folder here, you will find all the relevant data. The cases CSV and the DEMS cases CSV is the synthetic data that we will use for the input. We go again, 1 folder up. We go to the project folder again. We can go to the scripts folder, long COVID AI scripts, and here we find the relevant scripts from the GitHub repository. We will start with the first script, which is called mapdbmart CCSR ICD, which is used to take the input data table and map it from the ICD codes into the CCSR categories. Therefore, at first, we have to load in the first lines, we have to load the required packages. And afterwards, we have a choose directory function, which we need to load because that's depending on which subsystem which operating system you're using, the TLCTK package might not be available, and you might need another package to use this function. Okay, now we are coming to the relevant part. These 5 lines or 5 lines are the ones you have to modify, or if you are running the script. First, you need to add the site, so which site you are running. Currently, here is test. We can add like I2B2 workshop here, but you can enter whatever you want. It's just relevant for the naming of the files, so that you can later recognize your files, especially This was created with the idea in mind that you can run it at multiple sites and in the end then somehow compare the results. Then you need to execute this line after you changed it. You can do that with command enter, or control enter. And then you need to provide a lab test code, or if you have different lab tests for the COVID infection in your data, or if you have just an ICD code for that, you can also just provide the ICD code. That's what I did here, because in our synthetic data we just have a plain ICD code for the COVID infection. So that's the positive lab test code for the COVID infection. If you have here others, you can also just add them. So it's possible to add a list of codes here, so that if you have multiple codes, you can just add all your local codes here. Because these codes might be really different depending on each site. Then in the next, we also need to read in these lines, so we actually need to execute all the lines. Then in the next step, we need to enter the directory in which our data is available. So in our case, so if we execute this line, this pop-up window opens, we can select the data folder and click on select, and then it's done. We need to do the same for the output directory. So in this case, we are using the output folder for that. And then we are asking for the group. That's in our case, it's only the cases. If you also want to compute your own correlation matrices and all that stuff, you might need to also use cases, controls, or controls pre-pandemic. But in our case, we just have cases. So it's the cases group where we want to check if our patients have actually post-COVID or not. Then the input file, the file name is automatically created by just executing the next lines. This creates a file name, this one reads it, and then we also need to read in the CCSR mapping table, which is also provided in the scripts folder. So we just need to read it in. In the next lines, we now just transform the column names to upper to make it more uniform and easier for us to work with, so that we are sure that we have everything formatted in the same way, because depending on each system, you might have slightly different ways how to write stuff. So we just want to make sure that everything is written in the to uppercase. Yeah, and we also only want to keep unique lines in our input data. If you have data that's including the start date for a patient for the record is there multiple times, where then you just want to remove it to keep the memory footprint small. With the same thing we had in mind when we now calling here the garbage collector to remove everything. If you're going here on the environment, to remove everything that's not really used at the moment anymore, so that we make available, make most memory available. The next step is now only done for the cases, also for us, and that's where we now reading in, where we are checking in our read-in codes, where we're searching for the ICD code of the COVID infection or the available lab test codes. You might see here the ICD codes is provided with a dot in between. Ours was provided without one. We go here. So that's why I just provided as a lab test, because in some systems it's provided with a dot, in some system it's provided without a dot. It's really system dependent. So we have the default case that's provided with a dot, but it can also be just provided here as a lab test code without. Okay. And then it's here now checking that for all for all the COVID infections, we have at least 1 year of follow-up data so that we can to identify the post-COVID symptoms. And yeah, so we can just going here in this line 39 and just press Control Enter to execute the complete log. And in the end, we get all our cases encounters, how they are called, where we have at least 1 year of follow-up data, and also writing these files into the data directory as cases encounter. So if we now go in project in the data repository, the data, in the data repository, we now have it here like the COV parts R data was written today, just a minute ago. So that's just the data that we created, where we removed every patient or every infection where we did not have like 1 year follow-up data. Afterwards, we can actually do the mapping between the ICD-10 and the CCSR categories. Therefore, we can just merge the mapping table with our ICD table, with our data table, with our data encoded things. Then we can check if the mapping did not work. We would enter an NA value into the column. Now we can check the rate for the conversion. If you are able, how many of these code were we able to map? And if we decided that if we were not able to map more than 0.9% of the codes, we wanna so 90% of the codes, you should definitely check your data why you were not able to do that. In our case, everything is fine, because if we take a look at this value, we were able to map nearly all of the codes in here. So 0.981. So everything is fine here. Then in the next block, these are not so relevant. This is mostly creating some statistics about the demographics in your data. We can just go through it. Okay, now we get an error. But we can, the result did not work, but it's probably because something was not correctly. Because one of these, that error happened because one of these files is probably empty, and then he has problem in binding these together. But for now, we can just ignore it, because it's really just some summary data of the demographics, which are for now not relevant, but which we should fix before, if we wanna get somehow gather together the results of other people and wanna compare it with ours. So we can just go through it. In between, here's some housekeeping, so that this is just really comparing like what's like the charts. Now in the next step, what's the Charleston index, so that we filter for the Charleston index, that we get the average. Or here in this case, if a patient has more than one Charleston index in this I2B2 data, we get only one, so that we in the end can provide the average Charleston index of all the patients, and which is significantly which is relevant if you want to create like cases and control groups, and want to ensure that your cases and control have somewhat the same amount of comorbidities. Then they should also have over your cohorts the same average Charleston index. I can just go through it, and we can in the end, we see like we are creating the number that we are writing out the number of patients, the mean age, the standard deviation for the age, how many percentage of the patients were female, the mean Charleston index. And then we are also writing out how many unique CCSR concepts we used. And yeah, in the end, these temporary variables are just deleted. And then, yeah, we can just go through it because that's really just some descriptive data of our synthetic data for all the demographics. It's really similar. And then in the end, this data is just written out in CSV files. And if you want, we can also take a look here, for example, at table 1. That's just it's an overview about it, what the data we calculated in the last steps. As you see, it's really just an overview of some kind of the demographics. But that's already the first step. The most important part here was that we created this Cove parts R data so that now we knew all of our patient data is mapped to the CCSR categories, which is the main purpose of this file. And this summarizing information is just an overhead, which is nice if you want to compare this. Now we need to go to the scripts folder. Sorry. Now we need to go to the scripts folder, open the second file, case incidences, and yeah, open it. Okay, now we have it here. We could now just run it all by just pressing Control Enter once, but that's not what we want to do. We want to going to it step by step. Again, we need to at first to load all the required data. These packages should already be pre-installed for all of you, or they are not. Okay, it's interesting because I executed it just shortly. Okay, so now all of you also need to install that, but that's going fast. Most of the packages should already have been installed. Again, we are creating our choose directory function. We need to update our site. It's not test, it's I2B2 workshop. And now we need to load our data. In this case, it's the Cove parts file that we created in the previous script. That's in the data folder. You can just select it, click on open, and it should now be opened. And if we go in here, it should be now be CCSR cases encounters. Here it is. Here we have now our patient num, start date, and these are just the encounters. And the CCSR is everything mapped. It's a mapping from, the CCSR table is a mapping table. Okay. Okay, let's close these. Then again, we need to define the output directory. This is just the output folder. And again, to make it easier, we again transform the call names to lower and ensure that all the dates in our cases encounters, so for our COVID infections, here that the date is all also really recognized by R as a date and not as a string. This is a file we already closed. So we just need to transform it just to make sure, and also break down now the cases by quarters so that we see in which year and quarters is. That we have a column now for in which quarter these cases occurred. Now we just, for this file, we create a temporary file where we just take our encounters and which we need later for merging. And also for our cases encounters, we now group it by patient and these quarters, and ensure that we're only taking like 1 COVID infection per quarter for each patient. And now we only want to keep, okay, that's new. That's want to make it, okay, we need to restart. Let's restart the R session. Okay, it looks like we have to restart with this file. That's new. This morning it was running. Okay, again, we're executing this block here where we load all the required functions. That worked. Okay, then we use the site. Again, we are loading our file from the data repository, choosing our output directory. And yeah, let's go into this. Okay, this one is running. This also. Okay, that's where we crashed. Now we just, for us, we have 243 unique COVID infections in our data. So patients with, this is not the number of patients, actually that is the number of patients. We have 243 patients with at least 1 COVID infection in here. So what we did was like we get the unique, got all unique patient numbers from our cases and just got the length of it, how many these are. So it's just a count of how many patients have at least a COVID infection. It's just for us as a small information in between. And yeah, now we can also clean up the data. This is for that we only keep the first infection in the 90 days, where we just would probably remove every infection that occurred in 90 days after the first one. Yeah, that's a nice debug comment that you see here, boost loop speed by 100 times. There's something we wanna do, we somehow need to do because it's not the fastest, but it's actually quite fast. It's okay now. So again, we get all data from all our cases. We get all the unique cases. So we only get only get the data from the patient which are in our list of unique patients here. And again, we need to somehow transform or format the date column in the right format. Otherwise, because it's probably this is here because we run somewhere into errors later because the date was not formatted correctly. So we need to do that here. Otherwise, it crashes. Then we're creating an empty list here and start iterating over all the patients to just remove infections. Just iterating over all our patients and removing infections that are not, selective start date. Yeah, where we filtering that where the infection occurred more than less than 90 days. So that is a step where we now really ensure or filter out all the patients where the infection occurred less than 90 days after the infection. And that's just a loop that iterates over these 200 patients. It's fast enough on these 200 patients. It's getting slower if you have large amount of patients. That's why there was this speed up comment over it. Yeah. Then we create a data table from this list. And now remove those patients who do not have more than one positive COVID signal or COVID infection. It's now done in the next 5 lines. And then we list those patients who have multiple labs in this. Again, we need to somehow transform the state column again. Then we can bind these list of the case encounters together and write out all these data. So now we have only in this file only patients. It only contains the patient data, the data of the patients who had at least one COVID infection and only like one COVID infection per 90 days. So that we ensure that between each COVID infection are at least 90 days, and that's because otherwise we would assume that these multiple infections somehow belongs together. Now we are just creating some statistics over our data. And yeah, also writing these statistics out. We can also take a look at it, cohort summary. Where are they? Here it is. Here we see we have 111 infections are in on the first infection. We have 132 infections which are a second infection. Then we have, and that's, you see that this is synthetic data because these are the years in which the infections occur. Okay, this is not realistic, so that some are occurring like in 2003. Why we are going here to 2,200 years in the future is also interesting. Yeah, that's probably because we are just created synthetic data with Synthea, and it's just created a large amount of patients data set. And you see, we are finding COVID when it did not exist, and also in the future. So it's just the date. So, but you see, we get some summary here in the end. Now we come to the original applying of the WHO definition, so our translation from the English WHO definition to the post-COVID patterns, which is in the third file, refdxr. Again, we need to define some parameters. In here, it's again I2B2 workshop. We can leave param 1 and param 2. That's just some information that's nice to see later in the summary files if you want to sort your data. Then you have to provide a p-value, 0. For which these seem things as significant. A sparsity filter for the screening of the patterns, so we choose a really low one so that we remove only really sparse sequences, so events that occur later. Yeah, since we are working here in the POSIT cloud, the memory buffer and the core buffers are both set to 0, since we only have 1 core for each of you and only 3 gigabytes of memory. And if we add a buffer here, we have free memory, but also the compute costs getting increased. So we are just keeping it low here. So just setting for this one, we're setting the buffer of 0. If you want to run it on your own, maybe set it to a little bit higher, like some gigabytes, depending on your machine that you're using, so that if you have also other things running that you don't want to allocate all of this memory with your data and your patterns, because we have later a function which, if you have too many input data that you cannot fit it really into your memory, that we can chunk it and then run the algorithm on small chunks of the data, and then in the end bring it together. But yeah, that's just really a case, just really for those cases where you have so much data that you will run out of memory. If you put it all in there at once and just want to keep some if you split it in chunks, so that we have still some buffer left where you can also, yeah, like have your RStudio instance or something open and working without need to thinking about that you will run into memory issues just because you open another file or open another browser tab with our guide. Yeah. So we also need to run those. Okay, we did that. Then we need to set some other variables that are required and the seed. This is a Java parameter that's required for one of the later packages. And then you will probably have to, these packages, deeply and tidy are probably there. You probably need now to install Mello and TSPM Plus. That are two packages that we are using. Okay, for me, it's already there. Also TSPM Plus, for you it might be installing. Can someone give me feedback if it's installing for you guys? Because if it's installing, I would wait a second so that you can easier follow. Same, okay, good. So then you can just go on. So I don't know why these packages are there, but the other one, he installed the other ones. Yeah. So that's just loading the packages again, creating also choose directory function. And now we need to open a lot of files. These files, yeah, we will go one by one through them. The first one is a file with our data. So we go to the data directory and open our cov.pads.r data. The second one is our cases that were mapped to CCSR. So that is, if you're going again to the data, it's case mapped CCSR, in this case, I2B2 workshop and not test. So we can open those. Then we provide like these pre-computed correlations. So you don't need to compute them for yourself, but we did that already for you on these more than 200K patients overall. So we just need to load our correlations. So therefore, we need to go to the scripts on COVID AI. And the first one is the ref course. The second one is refj file name. That's the thresholds for the correlations for the COVID candidates, possible post-COVID candidates. That's also in the scripts folder. refj thresholds. And the other one is the list of all possible post-COVID candidates we identified. So all of the possible CCSR codes and corresponding numeric representation for TSPM Plus. So that's refj data. Yeah. And the last one is ref thanks lookup file. That's also in this folder. And this is relevant since TSPM Plus takes all the input data, so all our concepts that we map to CCSR, and sorts them alphabetically, and then assigns to them a numeric value that we are using later to calculating all these patterns, because that's just more efficient than using some kind of alphanumerical strings, which really get an issue if we're calculating these amount of patterns. But because if you're using a smaller data set, so as we do here, we might not have all possible CCSR codes into our data set. And then TSPM would assign another numeric value, which would then be in conflict with our correlation matrix, because then the lookup wouldn't fit anymore. So then the numeric codes for the concepts wouldn't fit. Therefore, we provide our lookup table as a reference, so that we can use that in the later steps, so that we just ensure that we have the correct numeric representation for each concept. Then we need to also define the output directory. That's again just the output folder. Yeah, now we are creating a lot of file names which are later used to either store the files, or in the case that we have so many files, that we have so many patient data that we cannot fit it all in the memory at the same time, so that we have all these chunks, that we can take them and write them out into these files. So this is just how these files should be named, and we are just creating the file names. So that's just a long list of file names and parameters for all this stuff. So that, and also how we in the end want to name our results file name. We are just here defining all the file names on top, so that we in the end, in the algorithm, in the script, just need to use the variable. Okay. Now the fun begins. At first, we need to load our data, our patient data. Then we need to load all the COVID incidents, or the COVID incidents of our patients, and the correlation matrix, and the lookup, and the list of the possible post-COVID symptoms. We just need to load all these files. And then we need to rename in the JH threshold correlations. We need to rename one column, and then we can go in here, where we also just do some administrative renaming, or bringing all the call names to lower, so that we can easier apply joins and so on later. Then we reduce the dbmart, so the input dbmart cases. We can open this file now. Currently, this is our input data that we want to use to mine the patterns for our patients. So here we have the ICD code, the domain, the start date, if it was mapped, the CCSR category, how the numeric description, how it is called, so what we are using here, and the official ICD description. So this is the CCSR description. And now we want to make that a little bit shorter, and only keeping the required columns that we need to apply the TSPM algorithm, which is the patient name, start date, and the thanks column. This is also why we renamed the column, one of the columns in before. And we need to call names. Yeah, we need to execute line 102. Then we remove the large file, which all the patient data to save some memory, which is now not so important, but if you're working with larger patient data, it's getting quite important that you're also starting to remove all the data that you don't need, because otherwise you really run into memory issues. That was something we really had when we were running it with these 80,000 patients or so on. We were really running into issues and had to run it in multiple chunks, even on a large machine with a large amount of memory. Yeah, then we only keeping all these COVID patients, all the COVID infections which larger than 5. So if if a patient of you has more than 5 COVID infections, the 6th and the 7th and so on are not counted anymore. You're only keeping the first 5 for each patient. Hopefully no one has that. So I don't want to imagine how that's to have COVID 5 times after each other, always with like more than 19 days in between that. So that's quite a lot of infections. Yeah, then we need to convert. Now we are then just renaming each COVID infection to infection as replacing the COVID infection with COVID infection 1, COVID 2, COVID 3, so that we can later see after which COVID infection actually our symptom occurred. So that we can not only say the symptom occurred after a COVID infection, but also this post-COVID infection occurred after the second infections, and which allows us later to group them by infection, see, okay, which symptoms are more likely to occur after the first COVID infection or after a second one, or what is the probability that you develop as post-COVID symptoms after the first COVID infection or after the second one. Yeah, then we need to convert a column again into the date format. That we need to do that most of the time, since we are always loading these files and are not always recognizing the date columns as dates. Sometimes it keeps them as a string, and then it would run into issues otherwise. So don't wonder why it's here in multiple files and in multiple lines, that we need to somehow convert some lines into the right file format. That's something we need to do, otherwise we just had here and would get an error message. Then we combine these COVID infections, patient num with our then we here combine in this line bind is we combine our dbmart with all the normal values from the I2B2, so with all the other patient records. Oops, where did we now jump? Now we jump too far. Here we are. Here we need to combine the dbmart with this list of the COVID infections per patient, where we take from the COV-PASC patients list only the patient name, start date, and FANX column. COV-PASC, if you take a look at it, has currently 6 columns, where we see like the patient number, the start date, the infection sequence, is it like the first or the second infection, the date, the date which when the COVID actually, we see here this is date, year, month. So the first 2 are the year, then the other one are the months. So we see which year, which month the infection occurred. Actually, that's the summary file that we saw before, where we had also like infections in the past, but in 2000 something and also in 201. This was probably also this file, this information. So in which year? So we are not seeing this data in the future and the past, but instead we are seeing it actually like that was like which year and which month it occurred, and then it's like how it's which Phoenix it's like stored here. If you are now going for infection 2, here we see that infection 2 is like encoded as COVID-2, and you can also see how much days are in between the first and the second infection. But to apply the TSPM algorithm, we only need the patient number, the start date, and the Phoenix, and therefore we're removing these other ones before handing this table to the TSPM algorithm. And that's what we are doing in this line. Then, if we have by some chance still some lines in here that are really equal, so where we have the complete values in all lines, we are removing those, and then we are also only keeping all entries which are in our Phoenix lookup, which means we only keeping CCSR codes or other codes that are also in our lookup table, because otherwise, if we would keep other entries, we would not have pre-calculated correlations for it, and therefore could not do apply the exclusion criteria. That's why we can only keep here like these pre-computed ones. Then we actually apply the TSPM plus algorithm, and now we will see if it's still, yeah. Okay, that's working. So now we transformed the dbMart to like a patient lookup, a Phoenix lookup, and a numeric dbMart, where now we see all patient number are represented as numbers, the Phoenix is represented as a number, and the start date is still there, which consumes way less memory as if we would, and also computational power if you can now compute all the patterns as if we would keep them as alphanumeric. Yeah. This is just for later that we can save now our Phoenix lookup with and compare to our local ones, which should not differ, but might differ. So that's just for debugging that we also save that. Then we also store the patient lookup table, so that we know which numeric representation we now have for each patient, that we can link that back together. Yeah, now we define the number of threads that should be used by TSPM plus, which is like the number of available cores minus our core buffers, which we set on 0 in the beginning because we only have one core available, and we don't want to subtract any core from that, because then with 0 cores it might be difficult to calculate anything. Then we are just merging, it's just to something again to reduce the memory footprint by merging the correlation threshold table with actually the possible Phoenix that we have available, so that we speed up later the lookups. So that's why we are dropping all entries in this table that is not related to that is not required, since this entry is not available in our patient table. So we take everything from our large correlation table, and that's everything that we don't need, because we don't have anything. If we have like some correlation value for something that starts with a specific pattern, with a specific event, and this event is not occurring in our current actually database, then we don't need to have that in our correlation table, and we can just drop it and remove and increase the speed for later on, increase the lookup, and reduce the memory footprint. Yeah. Then now we get a list of all possible of all for all the numeric representation for the COVID codes. Then we say that we want to have like 3 temporal buckets. The temporal duration and bit shifts are technical parameters, same as the length of Phoenix for the TSPM plus algorithm. Store sequences during the creation. We can also set that on to false since we don't want to save them. This is for the memory buffer for the chunking. And if we would have too less memory to calculate all our patterns as ones, we would now split our dbmart into different chunks and calculate all the patterns chunk by chunk. Luckily, we have enough memory available, so we can just do it in one chunk, but nevertheless, we will just do it, so just that you would look how it looks like, even if you have more data available. Then we need here to rename one of the columns in the J threshold correlation table to endfangs. Then we create a list of the possible post-COVID candidates, and then we are iterating over our chunks, which in this case is just 1. Because if we take a look, num of chunks, it's below here because it's just a normal value. Num of chunks is just 1, so we're looping over 1 chunk, but that's okay. Actually, if we want to go through that step by step, I have to. So actually, you would now just press Control Enter here and go execute it. And I did not. That's good that I did that because now we run into an issue that I did not create this variable. I told you about it, but I didn't press enter. So now we can do it again. Perfect. Okay, but let's go through it step by step. Otherwise, I just executed this once, otherwise it would be complex. Okay, what we are doing. Here at first we are getting the current chunk from the list of chunks and just storing it in one variable. Afterwards we call the garbage collector to free as much memory as possible because we are now mining here all the sequences that end with that ends with a specific Phoenix. So it's a given one. And if you remember, end Phoenix is in this case is a list of 29. What we see here is a list of 29 variables, which are, if we go up here, that should be, which is the list of all possible post-COVID infections that are in our threshold that are available, that are in our database. So we have 29 possible COVID infections. And now we want to mine all patterns that ends with one of these possible COVID infections. That's what we're doing here. So TSPM Plus is taking care for us for that. Before the sparsity screening, we end up with 20,000 sequences. Afterwards, we have still 9,000 left. And then we are going into this block where we just iterating over all the COVID infections. And here creating the pattern, creating the end fangs of the patterns. So for the COVID code in this case. So what we saw, we have we have different COVID codes. So we have like COVID infection 1 and COVID infection 2. And what we are here doing is, here we are recreating the numeric representation of this code, of this endfangs, of this the numeric representation of this code in the TSPM, in this numeric pattern representation of the pattern that starts with we start with something else and ends with this COVID infections. Then we are combining these together to just combining them together here. It's what's my sequence? Yeah. Jace are the COVID infections. So sorry. What we are doing here is that we are creating the numeric representation for the possible post-COVID infections, which is has a slightly different number of leading zeros depending on how the numeric representation of this COVID of this possible post-COVID symptom is. No, for the COVID infections here, yeah. That we are doing here, then we are going further down. Then we are sorting these by the COVID infections so that we start with the first infection so that we can then apply the correlations. Therefore, we merge our thresholds with our merged those course in our mind. Maybe let's take a look at course so that we are seeing CoreSec, seeing what we're talking about. Makes it a little bit easier. CoreSec, where it is. Where is? It's not in the list here because I wanted the complete stuff one by one. But I can get it in there. Can probably just execute it again. Yeah, perfect. Now we can take a look at CoreSec. So that's what the output that we get from the TSPM plus function. What we are getting here is the patient number. Then we get the sequence and the duration and the corresponding duration bucket and the endfangs. What is the endfangs? The last 7 digits of the last 7 digits of a sequence are the corresponding are for the encoding the endfangs, and the one before are encoding the start fangs of the pattern. So that's also why in the later step in here, where we created the COVID codes, we checked how many, if it's smaller 10, smaller, larger, smaller 100, or smaller than 1000, and adding the corresponding number of leading zeros. And this is just some formatting of this CoreSec table so that we can later apply the other stuff. And then we start excluding or removing entries from this CoreSec table by creating a list of possible post-COVID symptoms. As first, we will check. Now we have a list for each patient. JC3. Maybe let run that step by step so that you can see what happened here. It's better. So now if we take a look at JACE, JACE is a list of pattern of sequences that we have patterns that we have mined with the end fangs, the start fangs, and the duration, and this corresponding rho and p-value, and yeah, adjusted p-value for cutoffs. And now we are here, now can iterate over them, what we're doing here. So check if, yeah, we're only starting removing J's when the patient has a sequence that is J to COVID, because otherwise this pattern would occur after the after the infection. So that's currently we are starting only considering this J. Yeah. No. Wait. Give me a second. So everything that is, so if you don't have a J to COVID sequence, so if you have a J to COVID sequence, that means that this possible post-COVID candidate also occurred before the COVID infection. And then we check, then if if we have a pattern from X to J, and X to J is not significant, we will remove this pattern. And then we are doing in a parallel process. We are checking for each. We are now checking here for the COVID events, which is like here this parallel for each block. It's just the application of the exclusion criteria. So we're getting the sequence. From this sequence, we're getting the start and end lengths, getting the subset of our patient here. And then again, building the correct numeric representation for the possible COVID candidate. And then start the exclusion process, just checking if it's X to J, if we have X to J and it's significant, and so on, and just iterating over it. And yeah, I could try now to explain that all here on an understandable level, but probably take more than the half an hour we have left. So it's maybe better when we are not doing that. So, but after we applied this now, we are getting here a list of our long haulers. Oh, that's still in the loop. This is a list for each patient. And yeah, after we need to do this for each chunk, since we are did this here in chunks, we also need to run the next stuff in the loop, where we just combining then all this table of our long hauler patients, so all the patients as possible post-COVID, and can then take that and write that all together, and in the end append all these parameters and write them out. And we can take a look at this. We have the result is this long COVID list, which is the list of the 6 in our 200 patients. We found like 6 different symptoms, which is quite okay, because I think included like 7 different synthetic PASC symptoms into this list. So finding 6 of this is quite okay, because the others might be, we added them randomly and then might completely find that they might be excluded. And the other one, the long haulers file, is actually the list where we now also see it for each patient. It's quite a long parameter. So we here have the patient ID. We see what's the corresponding post-COVID symptom. And we see also, we see after which COVID infection is occurred based on the start things here. This is a COVID infection. And we see the duration bucket, but also the original duration of this pattern. So we know how many months after the infection this post-COVID symptom occur. And that's now like a patient-specific list of each of all these post-COVID symptoms. Yeah. That's the code, how to do it. And yeah, if you're going in here, no, yeah, I also have it here. So yeah, that's that. So I already showed the list here with all the references. Maybe let me move that one here. So we also have like the hands-on guide. So when we have the guide where you can go through, we have the GitHub repository and also the manuscript. So yeah, but then if you have any questions, feel free to ask. Otherwise, yeah, maybe let's go here. That's a good slide. If someone want to ask, so also to the code or in general to the algorithm.
All right, we'll read out one question from the Q&A from online.
Yeah.
Can this methodology be applied to other conditions or states? For example, rates of heart attack during COVID as people put off visits to PCP?
Yeah, that's actually what we are also working on now. We want to change it to identify unexplained chronic conditions. So currently what you saw, you need some kind of event that you need to, after which you start looking for these unexplained chronic conditions. This could just be like a time point. So you could say, or that could be another diagnosis. So you want to now find unexplained chronic condition after heart failure, then you choose heart failure as your start here as what would be here C1 or C2. This would then be like the ICD code or the ENACT code, CCSR category for heart failure. And then you can also find unexplained chronic condition after these symptoms. So you can extend it, and that's also something we are currently working on and want to do. Yeah.
One quick question.
Yeah, for sure.
Oh, just one quick question. What size of your database right now when people, entering? Roughly.
That would be a question for you. How large is your database? So maybe for the online people, 6 billion rows is the answer. So for the patient table.
Okay. And how many % or roughly they already on vaccinations?
Again, that's something, since I don't have direct access, since I'm not.
The reason I'm curious that I still, lingering around the, subject or patient, they, have vaccination and those they have not.
I think.
Yeah, I think probably large proportion of subject. Okay. Yeah, I believe probably a large proportion of patients, they had vaccinations. Is that right? Okay. From the other database, they have, the patient age within the range of, largely within the range of 35 to 49. And how does it compare to your database?
So we have a larger range. So actually it's something we saw that like the chance for younger females is higher to get post-COVID than for older ones. So it's also maybe something because why our results like differ from that what other people found. So for example, what we found that you see some patient subgroup where you find these symptoms more often. And for example, if you now compare that to other studies which are, for example, done on a other subset of patient or other set of patients, for example, if you take a look at the VA's database, that's just compare if you, it's difficult, it's more, there are not so many, it's other range of people in there. So with different range from the age, also from the sex, then we have different distributions there. And therefore, you probably find also like different number of post-COVID symptoms or so.
The last quick question is that, mostly they find respiratory symptoms, and the subject, background information, for instance, like obesity, having, pre-condition like asthma, diabetics, hypertension is most frequent. I don't know how does it compare to a database that I'm curious to know.
How that compares. So I think if this information is available, that would be in there. And if one of these symptoms is associated with these with the corresponding post-COVID symptoms, we would have a positive association, and therefore those would then be a reason to rule it out as a post-COVID, even if it might have been getting worse due to the COVID infection.
Yep, very good. Thank you.
Welcome. Yeah. There's a microphone. Then I don't have to repeat your question for the online people.
Well, I will ask different questions. So first, the symptoms, are you mostly based on structured data or, okay, so diagnosis. Okay, then.
It's based on the I2B2 data on the, Sean, how is it called, your research database at MGH? That's the foundation for the data.
Yeah, was it most structured data or is it already extracted from the nodes? Oh. Okay, okay. Then the second question, I noticed one of the output file, you grouped the symptoms based on different organ systems?
Yeah.
Okay, so what if some symptoms is hard to say which belongs? So you have a mapping of which one belongs?
So this one was just for the, if you see here, like on the bottom, was just for like the presentation, so that it's easier to group it. But we also get a list of symptoms, so you can, if it's difficult to group it like to one organ system or body system, or we still have the original list of symptoms, so you can also check for yourself. And even if you're saying, okay, I wouldn't count that in that group, yeah, then you can see that, and also you still see the original symptoms. So it's not like that we like cut out just a symptom because we don't think it belongs to a specific organ system.
Okay,
group.
Yeah, because earlier we had some question we were discussing under there.
Yeah, we
I
used
know.
CCSR mapping categories, so maybe that also is something which, where we lose some kind of information when we map from ICD-10 or an ECK code to CCSR, that we also already lose some kind of information. So that's something we also might be related to that, so that which makes them difficult to bring that in the right groups. But actually, CCSR originally was designed to make it a little bit clear, so that we have subgroups which are better, where we can like group together different codes, so that they still make sense in this group. So automatically.
Okay. Yeah, that's what we were wondering, because sometimes, I know earlier you were talking about it for persistent symptoms. So if some of the symptoms no longer happening, you probably saying that's not, persistent. But unfortunately, it could be same organ system, but appearing like different.
Yeah, so if it's only the same organ system, it might still have a different CCSR category code. So yeah.
Okay.
So it depends, but that's something that could have happened if you have like two slightly different ICD codes or something like that, and they were getting mapped to the same CCSR category, yeah, then it could be interpreted as an ongoing symptom.
Okay, okay.
Yeah.
Okay. Yeah, last thing, I just want to, so I guess the script, everything you have there, we could potentially load another set of data, for example, claims data, and run the
Yeah,
model.
that's actually why we have this Docker container and everything available, and also the guide, so that you can do that. And that's also what we, yeah, like want you to do. That's also why we presented it here, because we would love to hear them back, get some results that we can like compare also. So we are always open to cooperate on that basis. So, and that's also something,
Okay.
especially why we presented here, because it's like, well, all these people who have enact codes, we have already also the mapping from enact to CCSR available, which would then result in a really nice comparability of all these sites, so that you can really compare it
Okay,
quite well.
perfect. Love to have more conversation.
Yeah, for sure. Thank you for these questions.
Any other questions in the room?
I'm aware that there's been extensive work on inflammation and various innate and other immunity phenomena in relation to PASC. Has this been incorporated into your studies? Thinking specifically the work from Jim Heath, the Institute for Systems Biology in Seattle.
Good. So I think a good question, but I think specifically integrated it's not. So if you would have those inflammation marker available, we could probably do that, integrate it somehow, but currently I think it's not directly integrated.
Yeah, the best way to do that, Gil, would be to add the laboratory data for inflammation as markers into the analysis.
Yeah, we would need to have the markers and some categories, so that we can then calculate somehow the correlations between this. Yeah, but it should be possible to integrate that if you have these values available for all the patients. But you would need to have it available for a lot of patients, also for controls, so that we can calculate like good correlation values at first, and then we should be able to integrate it. So yeah, it's possible to extend it so that we could include probably inflammation values.
That's a good idea.
I think so.
Along the same directions, just along the same direction with your wonderful question, I love to have those biomarker, lab tests, from the central lab, like, human-specific CRP or some other, interleukin marker, but they are too expensive. I wonder, in the general practice, whether, when they have that kind of study, and how much lab data they are available for the.
That was obviously a research study. It was 2 or 3 years ago now. Multi-authors from James R. Heath. I think it was in Cell, but it might have been in something else. I can give you the name and we can look it up.
Thanks, yeah.
Earlier in your presentation, you used the Spearman rank correlation rather than the Pearson correlation. I wonder how you made that choice and why.
What was our main choice for that? It's a long time ago, so that's like 3 years ago. Something I cannot tell you right now. We need to think about it, but yeah. Thanks for the question.
Any other questions in the room? No? All right, how about a big round of applause for Jonas? Thank you very much.